All right, hello again, everybody. Let's go ahead and talk about Pascal's identity. So again, let's do the statement here. For n and r and z plus, where r is between 0 and n plus 1 choose r is equal to n choose r plus n choose r minus 1. Now, before we get into the proof, I'll just mention a little bit about Pascal's triangle, where you may have seen this already in high school. So Pascal's triangle is this, and I mentioned this in an earlier video, but just in case you've forgotten. What Pascal's triangle is you fill out ones down the side, and then to get the inner numbers here, you add the 2 above it. And that's exactly what the statement of the theorem is. Right? N plus 1 choose r is equal to n choose r plus n choose r minus 1. So the n choose r and the n choose r minus 1 are these two numbers, and you're using that to get this number here. 1 plus 1 is 2. This number, let's just see if I can get these right. And again, I always screw this up. 1 choose 1, 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose, yeah, that's right. So this is 2 choose 1, this is 1 choose 1, this is 1 choose 0, this is, I guess that's 0 choose 0. How many ways can you choose 0 things from 0 things? One way to do it. Choose none of them. 1 choose 0, 1 choose 1. And what this is 2 choose 1. And if you plug it into Pascal's identity, 2 choose 1 is equal to 1 choose 0 plus 1 choose 1. That's what Pascal's identity says. In the same way here, down here, 3 choose, so this is 2 choose 0. This is 3 choose 0. This number that's going to be here is 3 choose 1, and that's going to be 2 choose 0 plus 2 choose 1, which is 3. Same thing over here. This is 3 choose 2. This is 3 choose 3, and so on. Okay? So this is what Pascal's identity does. It lets you fill in Pascal's triangle. But let's go ahead and prove it. And we're going to prove it specifically using the combinatorial argument. Okay, the top way of proving it algebraically using the formulas, that is easy enough. I would think you can do it, and I think most people can do it coming out of high school. It just takes getting some denominators right, simplifying some fractions, that kind of stuff. It's pretty straightforward. The other way, using a combinatorial argument, is the trickier one. People have never seen a combinatorial argument coming out of high school before, so let's jump down to that. Okay. So, if we're going to start the proof, first off, let's create law of universal generalization. Let's create our n and r. So let n and r be in z plus with 0 is less than or equal to r is less than or equal to n. Then what I need to do is I'm counting n plus 1 choose r. That's what I'm interested in counting. How many is n plus 1 choose r? So what I'm going to do is I'm going to create a set of n plus 1 elements and count the r element subsets of S. So let S be a set of n plus 1 elements. Then, the left-hand side of Pascal's identity, n plus 1 choose r, is the number of subsets of S with exactly r elements. Okay? That's what we're dealing with here. So that number I want to count in a different way, and that's what I'm going to do now with this other argument. So I've got, there's a nice picture that goes along with this. Let me draw the picture. So here's my set S. I'm going to start by fixing some element X in S. So fix an element X in S. What I mean by that is just pick one out, and I'm going to name that one X, and I'm going to separate that one out from everybody else. Then what I've got here is I've got this X has been separated, and there's n plus 1 total in the set, so there's n left down here. Okay? Then how many ways can I create an R element subset of S? That's what I want to do. The number of R element subsets of S that don't contain X is, well, if it doesn't contain X, the number of R element subsets of S, well, if the ones that don't contain X, they're all down here. So out of the N elements that are left, I just need to choose R of them, right? Any subset of size R, right? There's a whole bunch of them here. And the number of ways I can do it is N choose R, because of the N elements that are down here, I need to choose R of them, and that's it. So there's N choose R ways to do that. The number of R element subsets of S that do contain X is what? Well, if it does contain X, so the R element subsets are these things. There's one here, right? There's another one here, right? Sets that do contain X. Well, if it contains X, I just need to ask, what are the other elements? I just need to identify what the other elements are. What I've got is there are N plus 1 elements in total here, but if it contains X, then I'm not choosing from X anymore, so I'm just choosing from N elements. And how many more do I need to choose? Well, not R anymore, because I'm looking at an R element subset here. And X is in there. X is already 1. So I just need R minus 1 many more. So the number of R element subsets of S that contain X is N. Out of all the N non-X's, choose R minus 1 elements to go with the X. Thus, N plus 1 choose R, the number of all R element subsets of S is equal to those that contain X plus those that don't contain X plus those that do contain X. And we're done. Okay? So that is a combinatorial proof. It involves creating sets, counting things, and just using basic counting techniques to do it. So that's what a combinatorial proof is, and you can see that this is substantially different from a algebraic proof, which is where we just use the formula and plug and chug until we get down the formula done. Okay? So we'll leave that there. Again, watch this over and over if you need to, and ask any questions that you need. Have a good one. We'll talk to you again.